Okay, welcome back, everyone. So this is our last lecture of today. Julio, please take it away.
Okay. Let's see. So the goal now is to start focusing our attention more on this classical regime, which is the one that everything is under control, still hard to compute, right? So we're saying that there's an interesting region, which is this region here, where we are not just doing kind of tree-level stupid perturbation theory, we're doing something more interesting, and also we're trying to compute radiation, things like that. So the idea is to understand how we can take, we can do these computations, how we can systematically expand in this classical regime and see which contributions matter, et cetera, et cetera. Okay? So since we are in the business of drawing these phase diagrams, I will draw yet another one, which is now the phase diagram purely in this classical regime. Okay, so this is phase diagram of classical GR. And now what we're going to have in mind, instead of this massless particle scattering, we're going to be a bit more concrete. We're really going to have in mind a pair of compact objects that have mass little m and big M. Again, they will be separated by some distance, r, or some impact parameter if they're scattering. Okay, and we're going to draw a phase diagram in terms of these parameters. This phase diagram is much simpler. So here we're just going to have kind of gm over b or gm over r. That's the same parameter that we had here. It's just the weak field parameter. Okay. Now, because we have some mass, we can take, say, the non-relativistic limit. Maybe these things are moving slowly. Actually, generically, if these are bound, then you will have that gm over r will be of the order of v squared by the virial theorem, right? So weak field will imply also a small velocity. So let's take the small velocity limit. This is still super Planckian, right? Because we said that the mass of the sun is like almost 40 orders of magnitude above m Planck, right? So we still need to worry about all of these nonlinearities or resonations, et cetera, if we are coming at this problem from scattering amplitudes. We'll see how that comes about, but okay, for now, this is just the weak field. And then the other axis is going to be the mass ratio, little m over big M, okay? And here, instead of some order parameter like there, I'm just going to tell you what tools we have available to solve this. And then we'll see how all of these things are realized in the particular, or at least some of them, the perturbative ones, are realized in the context of scattering amplitudes. Okay, so for instance, here again, there's some region, say, up when the mass ratios are order 1, maybe up to 10, or kind of 0.1, if we are, this is supposed to be a small parameter. And then when the field is strong, so when B is of order of the Schwarzschild radius, right? Here, now this is classical, so we do have some classical equation motion. We have Einstein's equations, and we can put them on a computer. So this is just numerical relativity, which now, since about 20 years ago, we can actually make predictions for this kind of mergers and stuff like that. Okay. Now, there's a region here. So now these boundaries are blurry. They don't have a particular slope. There's a region here where we have weak field expansions. Okay, so what are the weak field expansions? Well, we have this post-Newtonian expansion, which is the expansion when these parameters are small. For instance, for a bound system, we have gm over r is of order v squared, which is much smaller than 1. And there's also this post-Minkowskian expansion, where we just have that gm over r is much smaller than 1, but the velocities can be relativistic. Okay, So 1 here, it actually means the speed of light squared. Okay, so this is perturbation theory. It's perturbation theory in G Newton, also in velocity. So this should be amenable to perturbative techniques and to scattering amplitudes and all of that. And I'll try to explain how this comes about. Now the other interesting regime, so let me draw a picture here, by the way. So the picture here is that because this is very weak field, this just looks like kind of flat space-time with like 2 tiny objects perturbing it, and there's some ripples that this create that they mediate gravity between them and their dynamics, et cetera, okay? So this is really very weak field, where you just have the tiny gravitational field around each one of them. Okay, so now if the mass ratio is very large, then there's this other technique, which is called the self-force, or the probe limit, which is actually the leading order, right? So what does this look like? So when this mass is infinitely large compared to this one, this is just a probe moving in a background generated by this one. So for instance, this is some like big black hole. So now I have that the grid is all deformed. So here I have my big object, and then I have a very small object that perturbs this space-time, right? So the probe limit, this is just some black hole and kind of geodesic motion in this background. But it turns out that for many practical applications, we need to go beyond this probe approximation. And the self-force theory is just a systematic expansion in the mass ratio. It's just how we can solve Einstein's equation order by order in the mass ratio, where the leading order is just this geodesic motion in the background. But then we need to understand actually the gravitational field sourced by this small particle, which will be small as a perturbation, and how it acts on itself, how it affects its own motion, which is why it's called self-force. Okay. And we'll see later, again, in scattering amplitudes, how to count these powers of the masses and see which contribution is at which order in self-force. Okay. So just
if D becomes very small, then of course it becomes very big.
Sorry, you're right. Yeah, it's the other way around. You're completely correct, yeah. Okay, and by the way, note that these regimes, they're not only computable, but they're also not computable in numerical GR, okay? Because these are regimes where we have some large hierarchy, right? So for instance, numerical GR can do about order 10 mass ratio nowadays, right? But actually what we need, say for space detectors, is something like 10 to the 5, right? And the runtime goes like the square of the mass ratio in weeks. So this goes like something like 10 to the 10 weeks, right? So you need like a few billion years to compute numerically one of the waveforms for one of these events that we expect that have very large mass ratios.
You now indicate that if you have big mass ratio, you want to use self-force, right?
Yeah.
But I mean, the mass ratio will never be greater than 1, right? Because we will always say the bigger one is like the capital, right?
Well, it depends if you say this is the big one or this is the small one, right? Yeah. Then the axis goes in the other direction.
So you kind of say that the big axis is 1.
Yeah. So here, yeah, I guess I flipped both axes. Yeah. Yeah. So this is now 10. Okay, so now our goal now is how to understand kind of both of these perturbation theories by expanding some scattering amplitude, and also see how some of these comments that I made that we need to resum or we need to exponentiate and things like this come about. But okay, before I do that, let me just, for terminology, since we'll use this later. So what do we mean by discounting, right? So when we count powers of G or of the mass, right? So for instance, when we have some object, each correction in this mass ratio we'll call a cell force correction, right? So the cell force 0SF will be just the probe limit and then 1SF will be like the first correction that goes like m over m or little m over m, so that we have actually a small parameter, et cetera, et cetera. And 2SF will be the square of that. And similarly, when we do like post-Newtonian theory, so we have like 0 Pn, which is just Newton's potential. So it's just Gm over R, right? And then there will be like 1 Pn, which are the leading corrections to this. So this will be Gm over R times either V squared or Gm over R, et cetera, et cetera. Okay, so it's always relative to the leading order, right? And then if we do PM, then we're just going to count powers of Gm over R. So we'll have Gm over R 2 orders of velocity, Gm over R squared 2 orders of velocity. So let me not write that. Yes. Yes, that's right. So when we do scattering amplitudes, it won't be, we're going to do a double expansion in G Newton and in the masses, which, by the way, will be natural, because I was telling you that we do have a double expansion, right? We have this weak field expansion and expansion in Q over M, and we'll see that that Q over M expansion automatically separates things into different sectors in the mass ratio. So it's actually, yeah, everything is homogeneous in the masses, so we can very easily count which contributions come from where. All right. Any questions about this while I erase? Yeah, so actually, I'm not going to erase this. I'm just going to change it to what we're going to use now because we have massive objects. So now we're just going to have these scales here, Gm, and this is 1 over Q. So as before, we're going to have to count powers of two things. We're going to have to count powers of Q over M, which is much smaller than 1. And we're going to have to count powers of GMQ, which is also much smaller than, so this is the same as Gm over R, which is much smaller than 1. And you see that these precisely, powers of these are powers of the weak field. So this will implement this PM expansion. And this, I told you, is quantum versus classical, but because we're expanding in some mass ratio, we'll see that from this expansion, we'll be able to identify the different terms in cell force in a given diagram. Okay, because we will see how every time I expand, I'm going to change how many powers of one of the masses appear. Okay, so what is the intuition here? The intuition is that if we are interested in some classical process, when we compute the scattering amplitude won't be the correct quantity. As I mentioned, the scattering amplitude will be e to the I s over h bar, where this is this classical action, right? Well, generically, this will just be some action, right? And this is the thing that has some nice expansion, right? So this S will have some classical piece like first quantum correction, second quantum correction, et cetera, et cetera. And then these things here will be relative to S classical, right? So if I have S q to the n S classical, this will go like p over m the n. And on the other hand, the classical action itself, also the quantum ones, but we won't worry too much about those, this will have a free part, and then it will have like a 1 p.m., 2 p.m., et cetera, right? And these things will go like GMQ, or will be suppressed by relative powers of GMQ. Okay, so this is an expansion that goes like powers of GMQ to the n. Okay? So we have this double expansion, but the issue is that it's an expansion of the log of the amplitude, not of the amplitude. So when we expand the amplitude, we'll have to be careful to keep track of which terms come from where, because there can be terms here that come from expanding this exponential that can be overlapping of these different contributions. Okay, so now what we're going to do is we're going to start with some amplitude, see how we can expand, and try to identify some of these various terms. Okay, so both of these things involve an expansion in small q. So we just need to understand how to expand the amplitudes in small q. And so many things are going to be homogeneous in q, right? So the idea is that we could have some diagram. So let's draw some diagram. And we want to identify which pieces of these are interesting and which are not for this classical dynamics. Okay, so let me just give it some labels. So this is going to be Q, this is L, Q minus L, P1, P2, right? This will be P2 plus L. Okay. And the tool that we're going to use to understand these contributions is something that is called the method of regions. Which means that if you have some Feynman integral, so let's write what this looks like. Okay, so I'm going to have a pole that goes like 1 over q, right? I'm going to have the loop momento, so let's do this in 4 dimensions. I'm going to have 1 over L squared. 1 over L minus Q squared, and 1 over 2 P2 dot L plus L squared. And maybe some numerator that depends on these vertices, but actually I won't care too much about this. This depends on. Okay, so we want to understand the various contributions. So we want to expand in the limit where Q is much smaller than the P's, right? So the limit that we're interested in is Q much smaller than P, but the question is, what about L? Okay, so this diagram, in principle, we are integrating over all of the loop momenta. So we need to understand kind of the various contributions. So it could be that L is very large, L is order Q, L is order P, right? So each one of these scalings are called different regions, but not all of them will be interesting. Okay, so for instance, notice the following. So if I want to extract some contribution that looks like GM over R, right? That Fourier transform crucially relies on the fact that here there's an absolute value, okay? Because otherwise I don't have anything non-analytic. If I just have like Q mu, the Fourier transform of this will just be a derivative of a delta function at zero impact parameter. Right? So it will be some short distance contribution, whereas the Fourier transform of something like, for instance, 1 over q, this will go like 1 over b. Or the Fourier transform of q, this will be like 1 over b cubed. Okay, so I want to keep track of things which are non-analytic in Q. And remember, I said originally that those things are always interesting. They're always predictable. They have to do with some discontinuity. The coefficients are well-defined, whereas things which are short distance, things which are contact terms, might be ambiguous when we do gravitational calculations. Okay, so we might have some, we're going to compute some loops. There might be some UV divergences in these diagrams. We'll see later an example of this. But as long as it's a short distance contribution, when I do the Fourier transform, they're going to give me something which is a contact term in position space, so I can just ignore it because my particles are never going to probe this. So, okay, let's expand here now. So let's think first of the first region that we can imagine, which is where L is actually much bigger than Q. Okay. Okay, so if L is much bigger than Q, I can just expand away this thing here, right? So in this region, so let me call this the hard region. This goes like 1 over L squared plus corrections go like this. But the result now is a polynomial in Q. Okay, because Q, the only place where it appeared in this integral is in this denominator here. Here it might appear, but in a polynomial way, right? So this hard region means that if I expand this amplitude in this hard region, then this is going to be polynomial in Q, or analytic. So this is short distance. Okay, so I'm not interested in this region. So this the full quantum amplitude, this integral will receive a contribution from when L is much greater than Q, but it's going to be something that is going to look like derivatives of delta functions in position space. And I will never see that when I do some classical scattering process, so I might as well completely ignore this region. I can just throw it away. Okay. Now I'm going to look at the next region. So the other option, yeah, exactly. Great. So there's subregion, which is when L might be of order Q. Okay, because Q is already small, right? So let's just say that L is of order Q, right? And then let's see what happens. So if L is of order Q, then this thing here is homogeneous. This here is homogeneous. This one is not homogeneous because now we have something that goes like P dot L. So Q is much smaller than P. So this term here is bigger than this because this goes like Q squared now. So we have that 1 over 2, is it P2? P2 dot L. This term goes like PQ, but this term goes like Q squared. So again, I can expand it away. Okay? So this will go like 1 over 2 P2 dot L. And And then 1 plus order, the correction is order L squared P dot L, which indeed is Q over M. Okay, so that starts to look right. So now we do have an integral that we can compute at the leading order in this expansion, and we can see which kind of correction this is going to give us. So let's do it. So at the leading order, this integral that we had let me just do the scalar integral for simplicity. If you had a numerator, you can just do tensor reduction. Okay, so now this is very easy to understand how it scales under various things. So first of all, now this is homogeneous in P2, right? So I can write P2 equals M2 times some 4 velocity. And then this completely factors the dependence on the mass. Okay, so we know that this integral is going to go like 1 over M2, right? But then the only dimensionful quantity which is left is Q, right? Because P2 had dimensions, but it's homogeneous. So this can only be a non-trivial function of Q, but it's fixed by dimensional analysis. Okay, so let's count. So this will go like, L goes like Q, so this will go like Q to the D. And then I have 2 powers here, 2 powers here, and 1 power here. So this is D minus 5. Okay. So this integral goes like 1 over M2, 1 over Q, with some number that we could compute, but I won't bother, because I just want to understand how it scales. Okay. Now, I've done something a bit sneaky here, which is kind of the magic of this method of regions. Can someone guess what's funny about what I just did? So I just took an integral which has contributions from different regions of the integration domain. I just expanded away the integrand willy-nilly, and then I did the integral, and I declared that this is the answer. Yes?
I mean, you took the full integral, but you said that you strict the domain, right?
That's right.
And you also neglected the numerator, but I think that's fine.
Yeah, okay. So indeed, the numerator is fine, but the first thing that you mentioned is the subtlety, right? So here, I just did some integral, and then I didn't put any cutoff, right? So if I actually had the original integral, and then I said, okay, let me split this integral over L in the region kind of from 0 to some cutoff lambda, where lambda is kind of bigger than Q, and then the region where this is much bigger, right? Then in principle, I could have non-trivial functions of this cutoff here. Right, so I need to introduce some intermediate scale. So if I was doing calculations like this, then I would have to be careful. And in principle now, in addition to Q, so this is the subregion. So this is the integral from 0 to lambda, which maybe it's of order Q, but not exactly Q. So this could be this times some non-trivial function of Q over lambda, for instance. But the magic of the method of regions is that if we use dimensional regularization, and only if we use dimensional regularization as a way to compute these integrals, this is allowed most of the time. So what is the reason for this? Let's just imagine what happens if I now take the integrand, which I integrated over the whole domain, right? And this was the contribution that I was interested in, but now let me integrate it over the other region. Okay, so I already expanded the integrand, and now I'm going to do the integral over here. So if I now do the integral from lambda to infinity, okay, so what is the result of this? Okay, because now L is much bigger, so lambda is bigger than Q. And in most of the domain, now L is again much bigger than Q. I can expand away Q, just like before. Okay? So this thing actually will go like the same integral. But now this is homogeneous in L, and it's scaleless. And by definition, in dimensional realization, scaleless integrals are 0. If I don't have any dimensional quantity that this could depend on in the integrand, then this is 0, okay? So the fact that I'm integrating over the whole domain, it's fine, because the contribution from this other region, if I just extend this from minus infinity to plus infinity, is a scaleless integral, okay? Now this works most of the time. Sometimes you have to be careful. There can be an overlap that you need to subtract. So it's not guaranteed that when you expand now the soft integrand in the hard region, you get exactly 0. But in this case, it is true. Yes? It's homogeneous also. As I explained here, the dependence on M is homogeneous. Yeah. Yeah.
Like in the integram, there is also P.
No, it's P, but it's homogeneous in P, right? So we know how it scales with P. It cannot be a non-trivial function of P, because it's like any variable that the integrand is homogeneous on. It cannot be a non-trivial function, right? Because I know that. Let me put it this way. I know that P ddP of this thing. I know how it scales exactly, so I can just pull out the dependence. So it cannot be a non-trivial function. It can only be a trivial polynomial. Yeah. Okay, so this is the whole magic of the method of regions. Yes.
You also have to have lambda as something.
Well, but now I mean, I just introduced it to show that I had these two contributions, but when I did the integral, I didn't introduce it. Right? The point is that I did this integral over the whole domain, but the extra piece that I added is scaleless.
Yeah, but the argument that extra piece is trivial.
Yes.
But the argument is you kind of have to do some kind of cutoff.
No. I didn't. I'm still doing the whole integral, right? I'm just telling you. I integrate over the whole domain, but I didn't add anything, because if I added a cutoff, the result will be scaleless automatically. I'm not actually adding the cutoff. I'm just doing that whole integral and arguing that where L is much greater than Q doesn't contribute. Yeah. Maybe this way of writing it is not completely clear, but yeah. Yes.
I also have the same question. I think you're saying that the second integral that you declare to be 0 because it's the nucleus. The lower limit of the integral is lambda.
Yeah, okay, let me put it another way. So even in dimreg, right, this at worst could be some power divergence, okay, which we can tune to 0. So if you're actually using some regulator, you could play the same game, but then you will introduce kind of spurious power divergences that you would have to tune to 0 by hand, right? So in practice, what we do is we don't do this. We just integrate over the whole domain and argue that if the error that we would be making by extending this all the way to infinity, this is just the error. The error is the integral of this thing, or something like this. And this is 0. Yeah. Okay. So this is kind of the method of regions in a nutshell, but that has let us identify that this is the region that we are really interested in, okay? And now something nice about the method of region is that you could imagine, okay, what if there are other regions which are interesting? What, for instance, what if L is of order P? Or what if L is of order something else? You can always try. You can always take your integrand, expand, and see if you get something non-zero. And oftentimes what happens is that you just get something scaleless. So you can be exhaustive and just expand in all possible regions, and then do this exercise, expand the overlaps, see that if there's some overlap that you need to subtract, and you just compute the integral expanded by in various scales by taking all of these limits. Okay, so the summary is that the subregion is good because it's expanding in Q small and gives us contributions which are non-analytic. So here was this one example here. Okay. So actually, since we're at it, let's just finish here and power count the full thing to see that we get something reasonable in the context of this PM expansion. So let me now write actually the numerator, right? So the numerator coming from here, right? At most could be a couple powers of L or Q, right? So the numerator could be L squared or L dot Q, but anyway, in this subregion, this all scales like Q, right? And from these vertices here, at leading order, I would just have the momenta of this particle, right? So I would expect things that go like P2 to the fourth, because I have two vertices, right? So at the end of the day, what does this scale like? Okay, so we said that the scalar integral itself went like 1 over m2, 1 over q. Okay, let me put also the factors of g. So this will be g squared. I'm going to have p2 to the fourth, which is like the mass to the fourth, divided by 1 power of the mass. Here I'm going to have m1 squared. This will be like m1 squared, m2 squared, and then m2 over q. Okay, let's compare the tree-level diagram here. So this tree-level diagram, that would have given us the kind of leading contribution. This just goes like g m1 squared, m2 squared over q squared. So indeed, we see that this thing goes like g m1 squared, m2 squared over q squared, g m2 absolute value of q. So this is a post-Minkowskian correction. So this is the kind of this thing here, what's called this 1 PM, which is just the leading order, and all the relative orders will be higher powers of this. Now, you could ask, why do we stop there? Why don't we keep going? So we had this expansion here. So we expanded this guy here in this sub-region. We expanded away this L. So what would the correction look like? So the correction is just going to be powers of q over m, right? So the next correction, so we would have the same thing, m1 squared, m2 squared, or q squared. Here we had gm2q. But then if we kept the next order in the expansion in q over m, we would be multiplying this by q over m, right? So this would be multiplied by q over m. Okay, and we have to be careful because we still need to keep the non-analytic part. So what does this mean? This will give something that will go like g log of q. Okay, so is this quantum or classical? Okay, so let's think about the Fourier transform of this, right? So the Fourier transform, the 3D Fourier transform, okay, let me do it somewhere else, just to convince you. So if I take this goes like gm1 squared m2 squared over r. So this just looks, okay, except for an overall factor, it looks like the Newton's potential. Now if I do the Fourier transform of the next thing that I got, which was g m1 squared m2 cubed over q, is going to go like over r squared. So this is still a correction that goes like gm over r relative to the leading order, right? So so this goes like gm1 squared over r, and then g m2 over r. So this is some classical weak field correction. But now let's do the log. So now the log will look like, sorry, it's the whole thing that goes like the log, because I need to cancel. Here I have g squared, 1 squared, and 2 squared, log of q. So this goes like g 1 squared and 2 squared over r times g over r squared, which I can also write as g m1 squared and 2 squared over r times L Planck squared over r squared. Okay, so g just goes like Planck squared. So this is a quantum correction. Okay. Now, importantly, it's a computable quantum correction. I told you that anything which is non-analytic is still a prediction from the theory. Okay. But it's not something that we're going to measure anytime soon, okay? Because this is an extremely small number, right? But it's important to recognize that this is a prediction from low energy perturbative quantum gravity, which just gives me some correction to the potential between two particles that I can compute by just keeping higher and higher orders of this kind of quantum / classical expansion. Okay. Okay, so exercise, do this simpler diagram and recognize that it will also scale like this. Okay, so a loop of gravitons, you might expect that it's quantum, and indeed it's quantum, and it will give a very similar correction that will go like this, if you just do the calculation. Even from the leading order, here there's no.
If we detected these corrections, would we say that gravitons exist?
Yes. Yeah, I mean, this is really quantum gravity. Yeah.
I'd say, can we actually detect that there's
Well, there's direct detection and indirect detection, right? There's a graviton doing click in your detector, and yeah. Yeah.
It's more like we have like resulting power for the impact handle or the distance.
I mean, that's a real issue, yeah.
Yeah.
But yeah.
And we were detected in the most of one. Because we put in constant, I would suspect all those quantum corrections can never detect. They will always sublimate. That remains of quantum correction in the house. So they will always be advanced. Like the big quantum files, the class files, you don't need to take the class for file.
I mean, the question is this bigger or smaller than a very high power of this, right? And for fixed value of this, if it's smaller than 1, GM over R, there's always going to be a power that's going to be smaller than this. I mean, it's extremely tiny, so I think in principle it's not obvious. Yeah, but I don't think we're ever going to detect this in our lifetime for sure. Before the sun swallows the Earth, maybe. But what do you mean in a post-Minkowskian event?
Much smaller than a star, much smaller than the.
Yeah.
I would guess that these things we can never detect because it's always smaller than stars.
It will be smaller than the classical fields, but it will be a correction.
But it will be much smaller than 1.
It is much smaller than 1, yes. But I mean, there's a difference between parametrics and the real world, which everything has a finite value, right? Yeah, perturbation theory is always parametrics, but yeah. Yes.
I wanted to ask about what you said before for the method of regions, you could be just exhaustive and guess all regions and see if they contribute or not. But in, say, software linear effective theory, they're more complicated and momentum scaling.
Yeah.
There are more systematic ways to kind of say what regions
No. Yes. So it's a bit of an art. I mean, you use physics when you try to guess which regions contribute, and sometimes you can actually compute the integral, the full integral, and you can check that you have all the regions. But in general, it's a hard question. And later we'll see something more similar. So this is just kind of the overall scale of the loop momentum. But we also see when we start to think about velocity corrections that there's more interesting regions that are not completely homogeneous. Like each component of the loop momentum can scale differently. Yeah. Okay, more questions. Okay, so let me summarize the rules. So here I did it by an example, okay, where I actually computed the corrections, but I think it would be useful if I just summarize the rules. For the soft power counting, okay, so we have a graviton propagator. This is homogeneous, right? So this will go like 1 over q squared. If we have a matter propagator, right? This will go like 1 over the mass times q, because we said that this goes like p dot L typically. If we have like a matter graviton vertex, then at leading order, this will go like mass squared, but there's going to be corrections that go like q or L. So let me say this is q. Well, in general, this will be L. Q over m. Same here. So this will have corrections. So we can go to any order that we want. And then the last one is a 3 graviton vertex that just goes like q squared. And then the measure okay, so now with these very simple rules, you can just go to any diagram, expand it, and see kind of which pieces it contains. And I mean, calculating it is a different thing, but at least you can understand if it has like some classical correction, some quantum correction. But actually, there's a reason why I only discuss this triangle diagram and this bubble diagram first, because there are one extra complication. So what is the diagram that we missed? The box diagram. This is going to be a bit painful. Okay, so with these rules, it's very easy to expand. Okay, so let's just write it. So let's write it first unexpanded. And let's expand it to the leading order. Okay, and let's also put the numerator. So we already said that this might have a numerator, but at the leading order, okay, let me just write n for now. At the leading order, I can just put the mass of each particle. So this is going to go like what? Okay, so we're going to have m to the fourth for each particle coming from each one of these 4 vertices. So we're going to have g squared m1 to the fourth, m2 to the fourth. Now there's going to be each one of the matter propagators goes like 1 over mq. So I'm going to have 1 over m1q, 1 over m2q. And now the measure is going to give me a q to the fourth. And then I have 2 graviton propagators, which give me another q to the fourth. So this thing is going to go like g squared m1 squared, or m1 cubed, m2 cubed. Let's be a bit more careful. It might matter later. Okay, so we have a problem here. So the problem is that this goes like gm1 squared m2 squared over q squared. But the next term is, this is not suppressed. Okay, so instead of having gmq, I have gm1 m2. So this correction is large. This is not really small compared to, because remember g times m, g energy squared was large. Okay, so this looks like a very large correction, not as a small correction to what I had before. Limreg. Yeah. So this is 4 minus 2 epsilon. Okay. Notice, however, that if I expand to the subleading order, then I would get something reasonable, right? Because any correction to this will go like q over m. It would remove 1 power of m. I introduce 1 power of q. Okay, so then will give me something that looks very similar to what we computed here, which had a gm q. Okay, so it seems that inside of here, at some order subleading in the expansion, there are terms that look reasonable. They look like these classical weak field corrections, maybe some quantum correction, but at the leading order, there's this very large correction that that is a bit confusing. Okay, so any ideas about what's going on here? I kind of already told you maybe a half an hour ago, maybe a bit longer. Huh? What if I sum over?
Like exchange of 10 consecutive gravitational or something over there.
Well, those are going to give me more powers of g, right? But you're going in the right direction, for sure. Exactly, yeah. So remember, I told you that the thing that we need to compute to extract classical physics is not actually the amplitude, but it's the logarithm of the amplitude. Okay, that's the classical thing. Right, because remember that in this regime where we care about classical physics, we expect that the amplitude looks something, I guess sometimes I call it M, sometimes I call it A. Let me call it A again. And this goes something like e to the s over h bar, right? So we expect that there's going to be a term here. There's going to be terms in this expansion that come from just expanding this exponential, okay? So what do we know about this exponential? Okay, so let's think about it in impact parameter space. So we did a computation earlier of the Fourier transform of the tree-level amplitude, right? So this classical amplitude, we know that it started as, okay, we did it for massless, but now they're going to be massive. So remember, it went like gs over b to the d minus 4. So now here, s, let's just put m1, m2. Okay, maybe times some function of the velocity, of the relative velocity. Okay, and then b to the d minus 4, which is just log b. Then there's going to be a correction. There's going to be a correction, which is the 2D Fourier transform of 1 over q, which is what we computed here. So the correction to this classical thing, which we expect, is something that goes like gm1, m2, and then g m over b, maybe m1, m2. However, when I expand this exponential, I can get this squared. Okay? An exercise. Check that at this, by power counting, just these powers of q, that this kind of, this 2D Fourier transform of the leading order of the box this will give you a log squared of b. So that indeed we recognize that the leading term in this box just comes from expanding this exponential. Okay. So here we are seeing this issue that I was mentioning when I drew the phase diagram, which is that when we are trying to go beyond this Born approximation and probe classical physics, we're going to need to resum diagrams. This resumation is kind of trivial. We just need to take the logarithm of the amplitude. But every term in this S contains information about an infinite number of terms in the usual perturbative expansion of the amplitude. Okay, so here we saw the leading term of the box. But then if you look at these ladder integrals in general, so if you take the box plus this cross box, and next time we'll look at this particular combination and see even more explicitly how it exponentiates. And then you take all the possible permutations of the higher order terms, you will see that the leading order of all of these ladder integrals will just give you powers and powers of this log. Okay, so you will see explicitly the exponentiation of the amplitude if you compute these ladders. Okay, so yeah, you could either compute them and just see that they exponentiate, or next time we also talk about how one could compute directly the logarithm of the amplitude and see that this piece cancels. Okay, so I'm going much lower than I expected, but that's fine. So let me just mention what we will do next week, sorry, tomorrow morning. So tomorrow morning, we will just look in more detail about this Q over M expansion and identify the various terms that come with different powers of the mass and learn how to read off this self-force expansion and identify which classes of diagrams correspond to this probe motion of a particle in the background of some other particle, okay? And then we'll also think about how to do this velocity expansion. And if I have time, which it's looking less and less likely, we'll look at observables. But at the very least, I will teach you how to expand in all the parameters that this problem has. Okay, thanks.
Okay, any urgent questions? Okay, well, we already had enough questions, so let's thank again and call it a day. See you tomorrow, guys.